Well, you guys ready? Let's see here. I don't have the math battles to hand back to you guys. I think I'm going to let the grader grade those because after I took the mission away, I think she's kind of bored. She needs something to grade. So your math battle's the next obvious thing. And so of course we can talk about anything that was mysterious in there. I hope you've seen the solution posted there. Let's see here. I'll begin with a word of prayer once I get this board cleaned off. There we go. Dear Heavenly Father, we thank you again for this opportunity we have to meet and study your creation. And thank you for the rain. Just pray that you guide our steps today. Help us to glorify you when we do, Lord. In your name I pray, Lord Jesus. Amen. So, ask away if you've got questions. Is there a particular thing on the math battle you guys want to look at? Or mission 5, mission 4? See if I can find this thing. I didn't get a chance to I don't like my scan of mission 5. I'll try to redo that so you guys can have a better scan. It's the current scan. I use my phone. It's not great. Let's see here, lest I forget. Since I forgot the I don't think I have the attendance sheet today. So here's the top hat for you guys. It's 5898. Let's see here. So, come on. So here was the solution to the math battle. So we can talk about that for a minute, unless you guys got questions. So this is actually like test 2 that I gave, I think in like spring 2010 or something. But you know, the thing is, calculus is the same now as it is then. So there you go. So derivative square root is 1 over twice the square root. This is the power rule. Derivative of secant, secant tangent, cotangents minus cosecant squared is derivative. Derivative of log is 1 over x, e to the x, log 10 times 10 to the x. Derivative of cos is sinh, derivative of cosine is minus sine, minus 1 over x squared. And then I added like 4 more interesting ones, right? So, do you guys want to talk about the other ones that they're new? We can do that. Let's work out those together, make sure we're on the same page here. So the KLMN in the math battle, we have d dx of the square root of x times the square root of x. So how do you deal with that? All right, so what we're looking at is d dx of, you know, the square root of x times x to the 1/2, right? Which is, that's x to the what? 1 plus 1/2 is 3/2. So we have x to the 3/2 all to the what? To the 1/2 power. In other words, we're differentiating x to the 3/4. So the answer there would have been 3/4 x to the minus 1/4. So that would be k. L you've got yourself d dx of x plus x squared divided by the square root of x. Okay, so what we're dealing with there is d dx of x over the square root of x plus d dx of x squared over the square root of x. So that's d dx of x to the 1/2 plus d dx of x to the 3/2. Because 2 minus 1/2 is 3/2 and 1 minus 1/2 is 1/2. So that's how the laws of exponents work out there. And so what you got? You get yourself a 1 over, well, I'll just write it this way. 1/2 x to the minus 1/2 plus 3/2 x to the 1/2. And of course, you could rewrite that in terms of square root notation, but that's the heart of the matter, all right? That was L. How about M? Here we have d dx of 1 over x plus 10 to the 4th power, right? So I look at that as d dx of x plus 10 to the minus 4 power, and I use the chain rule, which in this case is kind of boring. Minus 4 times x plus 10 to the minus 5 times d dx of x plus 10. I don't even really write this half the time because, of course, the derivative of the inside function here is just 1, right? So in other words, you could write this as like minus 4 over x plus 10 to the 5th. Like oftentimes that's how you'd want to write the answer, but hey, what are you doing? Stop that. Just a second, let me, I don't know. What was that? Do you guys remember? The consensus seems to be 5898. That works? Okay. Yeah, sorry, I didn't remember it. This morning I was looking for my coat. I was like, where'd I put my coat? Finally, everyone convinced me it was in the car. I was like, I remember bringing it in, but apparently my memory is not from today. I mean, from yesterday. It's from like a previous day, right? Let's see here. So the next one is, never good to spray yourself with that stuff. Let's see here. Oh, look at this. This one looked tricky. We've got the cube root of x squared divided by the square root of x, differentiated. So this is n. So we've got d dx of the cube root, third root of x squared divided by the square root of x. All right, so what I'm going to do is I'm going to do the algebra before I try to differentiate, of course, right? So that is, what's x squared over the square root of x? That's what? X to the 2 minus 1/2, 3/2, right? X to the 3/2. And then we're taking the cube root of that. So that's the 1/3 power of all that. Then you multiply the exponents, and that gives us the derivative with respect to x of x to the 1/2. In other words, this is just a weird way of writing the square root. So 1 over twice the square root's the answer. There you go. Any questions about the second problem in the math battle? Yeah.
Can you explain when you put x as an exponent, you take the derivative?
How I x.
When you showed the first original 8 problems and the last one
Oh, sure. Like the derivative with respect to x of a to the x, where a is any base, right? We worked it out. It's the natural log of a times a to the x. So like d dx of 10 to the x is equal to the natural log of 10 times 10 to the x. It's just that. When we have, like, when a is equal to e, then you got natural log of e as the multiplier, which just is 1. So like we see this most often with the exponential, where we don't get that pesky multiplier of like the log of the base. But generally speaking, we have to multiply by the natural log of the base. That can be derived from like implicit differentiation, right? If you forget about it, you do this. I'll do it down here. You do y equals 10 to the x. Take the natural log of both sides. Differentiate implicitly, we get 1 over y dy dx is equal to log 10, which then gives me that dy dx equals to log 10 times y, but y here is 10 to the x. So like if you forget that, you can always derive it with implicit differentiation. Yeah, like implicit differentiation will allow us to remember so many things. Like if you're not good at memorizing things, if you're good at deriving things, you can get much. You can get a lot from that. So this one here, we had f over g prime of minus 3. And so I did the quotient rule, like f prime minus 3 g prime, g of minus 3 minus f of minus 3 g prime of minus 3 divided by g of minus 3 squared. And you just have to look at the graph, basically. The slope of f at minus 3, 1, 2, 3, the slope of f is up here, about 1/2, whereas the slope of g at minus 3 is about 2. And so that's why I put in the 1/2 and the 2 here. And the values are respectively minus 1 and 3 for g and f. So that's why I put the g of minus 1. G of minus 3 is minus 1, and f of minus 3 is 3. And so that's why that. This, on the other hand, is the chain rule. And the chain rule only is going to make sense if all of the derivatives involved exist. But g prime of 3 it doesn't exist. See, because there's a corner in the graph right there. So the derivative doesn't exist right there. So therefore, the derivative of the composite also does not exist at that point. All right. Problem 3 was problem 12 on your math battle. So some of the problems are like reordered, but if you've forgotten what the math battle was, I posted a blank copy of it in the math battle assignment in Canvas. It's there, and I do have a couple of extra copies of it here. If anybody, I have one extra copy. Anybody want it? Math battle. Okay, cool. Let's see here. Any questions about any? I mean, you guys ask whatever you want about. I mean, do you want me to do problem 3 in the math battle? I also don't have the solution posted for that either. That one's the case-wise defined function. I'll probably look at that for a second here. So for a function, the main theorem we had that's helpful for a problem like problem 3 on the math battle, which I probably should put up on the screen. Let me find it here. One moment. Sorry, I don't have a color printer. Wouldn't that make it nice? Oh well. So here we have f of x. So it's case-wise defined, right? We got sine of bx for x less than 0. And we've got x squared plus 3x plus c for x greater than or equal to 0. And we're supposed to choose, constants for b and c, which make it differentiable in R. So first of all, here's the easy part. Like f prime of x would be what? It would be b cosine bx, and down here 2x plus 3. This would be for x less than 0, and this would be for x greater than 0. Well, I guess it has to throw in the equality here if it's going to work, you know? So in order for that to make sense, in order for this, well, how to say this? So we, on the one hand, we need the limit as x approaches 0 from the left of like sine of bx to be equal to the limit as x approaches 0 from the right of the x squared plus 3x plus c, right? And that also has to be, well, anyway, so that has, we have to have the right and left limits of the function exist at the gluing point, because if it's differentiable at that point, it must be continuous at the point, right? Like differentiable implies continuous for f. And for the derivative to exist, we also need that the left and right limits of the derivative must match up as well, right? In other words, for the derivative at 0 to exist. So we need the limit as x goes to 0 from the left of b cosine bx. We need that to be equal to the limit as x approaches 0 from the right of, well, 2x plus 3. So these are the conditions which are needed for respectively continuity and differentiability. Okay? And so what do those tell you about B and C? Let me switch colors here for a second. From the top equation, we get what? Limit as x goes to 0 of sine of bx is what? If you answer, I won't tell anybody you're a nerd. It's okay. No? Physics told me that my son was a nerd the other day, because I told him about his dislike of fractions. He says that a fraction's an off-brand number. Somebody in my physics was like, "Sir, tell your son he's a nerd." I was like, "Okay." He didn't like it. What's that? You say what?
Sine of 0.
Sine of 0, which is? Zero. Sine of 0 is 0. We should not need a calculator for this. This we should know. All right, so sine of 0 is 0. And on the other hand, this one is what? 0, 0, c. So 0 equals to c. Aha. Apparently, c is equal to 0. Well, there's one down. Okay. And how about the other? This second equation tells me what's the limit as x goes to 0 from the left of b cosine bx. What's that give you? What's that? Yeah, just b, because cosine of 0 is 1. Very good. B equals to what? 3. And there you go. That was it. You choose b equals to 3 and c equals to 0. That makes that function differentiable on the reals. Because it's obviously differentiable in each of the cases. The only real issue is where the two cases join. Do we actually have continuity and differentiability there? All right? What do you think? Is this function twice differentiable on the reals? What if we were to calculate f prime prime? What would that be? We'd have what? Minus b squared sine bx. And down here we'd get 2, right? I think there is no hope for the second derivative at 0. See, because from the right we have a second derivative of 2, but from the left we've got a second derivative of 0. So this would be an example of a function which is once differentiable, but not twice differentiable at 0. That can happen. Other questions? Let's go back to the basic stuff here. Actually, let me switch over here to the homework. If I can find it. Ah! Computer's too smart for itself sometimes. All right. So any questions in here? So like, first of all, this one, the fourth root of 16 times x is the fourth root of 16, which is 2, times the fourth root of x, which is x to the 1/4. So like, that's how that goes. All right. This one here, again, if you're using the quotient rule, you're doing it wrong. Don't use the quotient rule for this. This is not a quotient rule problem. This is a do algebra, then differentiate problem. Right? We need the quotient rule when we have like a sum in the denominator, then you can't do this. Right? Like I can't, for example, if I was up against for instance, the derivative with respect to x of, say, x squared plus x cubed over x plus 3. See, there I can't do the kind of thing I'm doing in part B. There's no way to nicely break up this into, well, I mean, you can break it up into fractions, but the two fractions would be like x squared over x plus 3 and x cubed over x plus 3, and neither of those is really easier than what we're already facing. So we might as well just do the quotient rule for this one. But it's you know, so this one, you'd have 2x plus 3x squared times x plus 3 minus the derivative of x plus 3 was 1 times x squared plus x cubed divided by x plus 3 quantity squared. And so like, if I'm not simplifying my answer, there you go, we're done, all right? Don't fall for the trap here, right? So like maybe some of you in your homework have put 3 pi squared. No, pi is not a variable, right? Pi is a number, 3.14 blah, blah, blah. So when you differentiate that with respect to x, that's just 0. On the other hand, x to the pi differentiates to pi x to the pi minus 1 by the power rule. This one, part E, is a lot like what we just went through in the math battle, right? When we've got square root of 2 of the square root of 3x, I pull out, this becomes square root of 3 times the square root of x, right? But then I can pull out the square root of 2 times the square root of 3 from that. So I've just pulled this constant out, and I'm left with that. But that is x to the 1/2 to the 1/2, also known as x to the quarter, which then I can differentiate, and I get this. So this one here, you don't need the quotient rule for. You just do algebra. So because there's a single term in the denominator, we can simplify. We have 3x over that minus 2 over x squared over that. Now I just clean this up down here to that. Going from here to here, division in the denominator is multiplication in the numerator. So this is 2 times that, which is 2 times x to the 3/2. And then I get 2 times 2 is 4. X to the minus 2 times x to the 1/2 gives me x to the minus 3/2. So it gives you that. And then we can differentiate this by the power rule. Notice that like 3 times 6 over 2 is 18 over 2, which is 9. 3 times 4 over 2 is 12 over 2, which is 6. The minus and the minus cancels. So these are like what? So what do we do here? Product rule, right? Notice the derivative of 2 to the x is log 2 times 2 to the x. There's that derivative rule again, right? And what happens to the 2? It's gone, right? It just differentiates to 0. And like so. So then we have a product rule. So the derivative of the 2 to the x times x squared plus the derivative of x squared, which is 2 to the x times 2 to the x. And then in my solutions, if I've got like one underlined in one box, it's like, I'm like, this is an answer. That's kind of a better answer, right? Let's see here. If in doubt about whether or not I want you to simplify, just ask me, okay? And here is the product rule. So I've got the derivative of x squared is 2x times that sign. And then I've got x squared times the derivative of the sign, which is, first of all, cosine of the inside function. But then I have to differentiate the inside function. But notice that the inside function here is itself a product. So I have to do the product rule here, and that gives me that mess, which I can't read from here. ba x to the b minus 1 e to the minus cx minus ca x to the b e to the minus cx. That c is from the chain rule on the exponential. That b is from the chain rule on the x to the b minus 1 function. Wait a minute. Oh yeah, that's fine, it's fine. Never mind me. It's not the chain rule, it's just the power rule. Power rule on x to the b. Part E there, I think I've mentioned to you this guys before, but sometimes I find the chain rule, in terms of producing nice formulas, it's nicer to kind of do it inside out as opposed to outside in. So the inside out chain rule, I think about the innermost function, which is this, right? The derivative of this with respect to theta is c, so that's why I put a c there. Then next up I've got, a times tangent. So that produces an a and a secant squared, all right? And then finally I've reached the outside function, sine, which gives me a derivative of cosine times that. So, sometimes I do the outside function's derivative times the derivative of the next inside function times the derivative of the innermost function. But you can, you can either peel the onion from the outside in or from inside out, right? No, this is where the analogy of chain rule and onion breaks down, right? Yeah. So I'm just saying. Okay, I want to skip back over to the quiz unless you guys have a particular question, because there was a mistake I just thought about you guys made on the quiz. We haven't talked about the quiz in class. Let's do that for a moment. So, some of you got problem 1 on the quiz, and that's good. There's definitely going to be a problem kind of sort of like this possibly on the test. Now this one was different than the ones we've done in class, admittedly. So like, why? What's the weird thing I did here? I put the square root on the totality of the expression, right? So basically that pulls a half out by the properties of logs. That overall half, so I get log is, natural log of y is 1/2 times the log of all that. But then I know what to do there. That's like the class examples that we did already, right? There's a 5 from this, there's a 7 from that, there's a -3 from that, and the half multiplies through. I differentiate, and then I multiply by y, answer. So there's that. This one here, some of you are just trying to directly differentiate it. There's no direct differentiation rule for x to the x to the tangent, x to the x times tangent. Like you have to do the implicit differentiation thing here. So we take the natural log of both sides. We get log of y is log of that, which is x tangent x times log x. This is the product of not 1, not 2, but 3 functions. So I have to use the triple product rule, which gives me x log x plus x secant squared x log x by the derivative of tangent secant squared. Then the derivative of log is 1/x. So this 1/x and that x be canceling, just leaves us a tangent. So we get tangent log x secant squared log plus tangent all times x to the x tangent. X is the answer for that one. Once you understand the technique, these are not hard, but if you're not doing it that way, you're just making stuff up, which would just be totally wrong. Yeah.
What are you looking at?
Oh, this is quiz 6? Yeah. So I think in retrospect, I think maybe like 3 of you have this mistake. I'm not sure. I don't remember exactly, but a lot of you had like a like a +2 here or something. Do you know where that came from? For those of you who had like a +2 here in your quiz 6. Where it came from was in the original differentiation. For whatever reason, when you differentiated this, you just left the 2 there. I think that happened to a few of you. But that shouldn't happen, right? When we differentiate 2, we get 0. And so that's why it goes like this. But I think if you had a +2 here, I think what you did was you just forgot that when you differentiate 2, you should get 0 up here. Anyway, that was just a comment. So how do we find dy dx for a equation? We differentiate the equation. Remember to put dy dx anytime you're looking at a function of an expression of y. Chain rule demands we multiply by dy dx in such place. And after you do that, put all your dy dx terms to one side, put everything without the dy dx to the other side, factor out dy dx, and solve for dy dx. After that, if you're given a specific point and asked to find the equation of the tangent line there, you just plug the point in. This means x equals -1 and y equals 1. So I get -1 cubed minus 1 cubed divided by 3 times -1 to the 4th, 1 squared, and then 2 times 1, which ends up giving me 4/5 because I get a minus and a minus, which gives me a plus, and this is plus down here, so 4/5, and there's your tangent line. And here's the sliding ladder problem. We talked about that in class. It's in your homework, right? I don't know. I like this. This I think is my favorite related rates problem, honestly, because it's relatively simple, but I don't think it's altogether obvious. I don't think if you just asked many middle schoolers, if you told them the problem, you said, suppose the ladder's falling down at this rate when it's that far, I don't think they could tell you the answer. I really think without calculus, you're probably not going to guess the answer here. So I think that makes it an interesting example for me. Sometimes we do stuff in calculus, especially in the material that comes after test 2. There's some problems which have really beautiful answers that anybody could guess without calculus. And that kind of takes the wind out of my sails a little bit. When like a middle schooler can just guess my answer, it's not as awesome. I got 8.485 for that. So again, the steps for a related rates problem: write down the relation that relates the variables, differentiate with respect to time, all right, and then use what you're given. In this one, we're given that it's sliding down at a rate of 3 when the base of the ladder is 5 feet away from the wall. So I've got x equals to 5. I've got dy dt equals -3. And if I know x is equal to 5, I can figure out what y is, right? Because if x is equal to 5, y has to be the square root of 225 minus x squared, which is the square root of 200. So lo and behold, I get minus the square root of 200 times -3 divided by 5, which gives me that, which is approximately, like I said, 8.485. Well, I'll shut up. Are there any questions? Nobody? All right, well, so tomorrow we have test 2, so I hope you'll be here. Wish you well. Make sure you study the 3 proofs I mentioned. What were those 3 proofs? Do you guys remember? So the missions that are relevant are what? Missions what? Mission 4 and 5, is it? Is there just 2 missions for this one? Let's see here. If we look at mission 4, if I can find it, I would point out. Where'd you go? Come on, mission 4. Show yourself. Oh, there it is. So let's see here. Problem 188. So I gave an argument in class which I think is easier, but it's only easier to me because I am not afraid of the method of Carathéodory. To me, it's natural. To you, it might not be. And so for some of you, this is a more natural argument to prove the product rule, which is like the difference quotient for the product is the sum, like the difference of the products at a plus h and a. And then there's a sneaky step, though. You add 0 strategically. You add 0 there in order to create a difference quotient for f and a difference quotient for g, respectively here. And then you use the product of the limits as the limit of the products, and you use the continuity of the g function here to get the g of a, to get f prime of a, to get... So this is the standard proof of the product rule that you'll see in most calculus classes. It wasn't the proof I gave in class. And then the other thing you should review is we went over in class a careful proof of the, the derivative of sine and cosine, right? How did we show that the derivative of sine was cosine and derivative of cosine was minus sine? Do you guys remember what was involved there? I don't know if I had a homework problem with that or not, but I may have. Was it mission 5 or was it like mission 3? Was it earlier?
I know we went over it in class.
We definitely went over it in class. It was earlier, so that was actually a blast from the past, huh? So when I said that the test mostly focuses on missions 4 and 5, it is with the understanding that there might, I guess it's possible that this, I specifically said that this problem, did that on here? Oh, I don't know where it is, but it is definitely in here. I'll show you. Derivatives of sine and cosine right here, right? So what I was saying in my announcement was that you're allowed to know for that proof, you're allowed to know this, that the limit of x goes to 0 of like cosine x minus 1 over x is equal to 0. Maybe you'd see it with h, like limit as h goes to 0, cosine h minus 1 over h is 0. And also that the limit of sine h over h as h goes to 0 is 1. Those two limits we derive by a squeeze theorem argument like here. And, oh man, look at that. Ah, rats. I did do it in class though. I really did. Oh well, it's not in the, I hope you took notes that day, I guess is what I'm saying. Sorry guys. Anyway, I guess that's it for today. But you need to use the adding angles formulas for sine and cosine there, right? So you probably should look that up, I suppose.